Hello everyone, my name is Daniel and I'm a programmer and an artist. Today I'm going to walk through my array one-dimensional node and show how it's all put together. This morning there was a comment I saw that someone was asking if I could show how I made it. I think they're specifically interested in sort of how the UVs work on that. And since I needed an idea for a video anyway, I thought that would be a fine topic. So, it's fairly simple for the most part. This is the entire array 1D node group. The only complicated part of that is this node here, which I use in all of the array nodes to fix the UVs or offset the UVs, similar to how the mesh was offset. So we'll go through that as well. This outer layer sort of handles the 3D portion, and then this node, inner node here, handles the UVs. So the goal of what the modifier can do is pretty simple. It's just going to copy objects along an axis, basically, and we can add some additional options in there to give a reason to use it over the array modifier that comes with Blender. And the main ones I was interested in were rotation. There's sort of a basic version of a radial array can be done with it by rotating if you offset the origin point, or you can rotate each individual instance, where you see that here, where if this one's horizontal, this one's vertical. And then also I wanted with the UVs to make it so that the adjustment of the UVs could be more predictable, because when you set the UV offset in the standard array modifier, a value of 1 moves each copy of the mesh's UVs over one UV space. So a value of 1 in the offset means it ends up in the same relative position that it started in. So instead, what I've done on my array node is, if you say your UVs were scaled down or something, then a value of 1 in the offset on X, say, would move the next copy's UVs from here over one size of the UV island, basically, if that makes sense. So that's the goal of what I wanted to do with the node group. Let's walk through and see how we might do that. So the basic idea is we're going to take some geometry and we're going to turn it into an instance, and we're going to copy it, make a bunch of duplicates of that instance, and then we're going to position the duplicates of those instances based on whatever offset values are provided, and we can do some other translations like rotation or whatever, with some optional features, whether we output a mesh or instances, and if we do output a mesh, do we merge the vertices? Those are just sort of options. Alright, for the node group, first thing we're going to need to do is we have the geometry. We want to make the geometry an instance so that we can make copies of it. The number of copies we want to make is based on the count, which is the main setting of the array modifier. And then once we have those copies, we're going to want to move them around. So the very first thing I'm going to do is I'm going to rotate them based on the rotation value. So if you change the rotation here, you can see that affects the output. And the way that works is pretty simple. We have a value here. The duplicate index is going to start at 0 and go up to 1 less than whatever the count value we provide is. And they'll be different for each instance, each copy of the instance. So if we just scale the rotation by that value, then each additional copy will be rotated another 9 degrees in this case, or whatever the case may be. So if you do like 45, it'll be 45, 90, etc. So to do that, we just have this rotation, which is a Euler value, XYZ rotations. We're going to scale it by which copy we are in the array, and then we can just plug that right into the rotation socket for a rotate instances node. And I have that in local space, although in this case I don't think it would matter because all the duplicates would be at the origin anyway. So that's for the rotation. Next we want to set the position. So this is where we actually move the object, whatever this offset value is. However, we need to consider if we're doing relative or absolute offsets, and then do something different accordingly. So we have that menu switch here. What type of offset are we doing? Let's just convert that to a Boolean value. It was originally a Boolean value before there was the menu switch. I could actually change this to a vector and run it through that directly, but since I and it was just easier to do that. So if we're using the absolute option, then we're just going to use the offset value directly. That's going to go directly into the scale. We're going to scale by our duplicate index, and that's going to be our offset for the set position node. So that's this one here. If we set it to 1, then each of these instances, the origin point will be exactly 1 meter from the previous one. If we set it to relative, we first have to figure out how big the object is on all of the different axes, and then we can offset it by that amount. So to do that, we again have our geometry. We're going to use a bounding box node to subtract the maximum point from the minimum point, which will get us the size, the total size from the bottom left corner to the top right corner, essentially. And then we can multiply that those different XYZ values for the different dimensions of the object by our offset vector, and then pass that through the switch to multiply it times our duplicate index, and that will be our offset. Then once we've set the position, there's just some nodes to handle the different options that we have for the realize and the merge verts. So we have a switch here for the geometry. If realize is false, we don't do anything. We just pass straight through. Otherwise, we use this realize instances node to turn the instances into geometry. Then we might want to edit the UVs. Actually, I just realized we don't get, this could probably go through like that because we don't need that if there's still instances, obviously. Also, I just realized I probably should have done this the other way. The realize should probably be after, but I don't think it really matters. If you have realize off and merge verts is on, it'll pass through these nodes, but nothing will happen because merge by distance, actually that's not true, it would work. So it would be better, I'll probably update this to move this option after that. Anyway, but same thing here, there's just a switch to pass the original geometry through or merge it depending on whether or not we want to merge the verts. And then once we have all of that, there's one final option, exactly the same thing. We either pass the value straight through to the output, or we store a UV map on it, depending on whether adjust UVs is checked. And then this last node here displays a warning message if there's no geometry output. So for the UVs, what we have to do is, it's mostly just a bunch of parameters, so the name and the offset values. And the point of the UV adjustment node is to offset the UVs by whatever amount is necessary to keep the pattern seamless, basically. So you can see that even though we just have a simple checker texture here, we still have that problem where it doesn't tile perfectly right here because we have two dark cells at the bottom in a row, where if we wanted the pattern to continue seamlessly, which would be a light cell. So we can fix that by adjusting the UVs, and obviously we have to merge the vertices and realize the instances to be able to do that. So let's go ahead and take a look at how we do that inside of this adjust UVs node group. First thing we do is we're going to take in our array element, which is our face in this case, and we need to know later which face this originally belonged to, because we're going to convert the mesh into the UV map, basically, so that we can do things like bounding boxes on the UV map. And to do that, we have to split the faces apart, split the edges, which means all the faces get separated, and then we're going to arrange them based on how the UV map is laid out, and they're going to get split into instances and then merge back together. So by the time all of that is done, the chances that the indices of the faces have changed is pretty high. So because of that, we're going to capture the index of the face on the face before we do any of that, which means once we've done all of that splitting and merging and everything, we can evaluate based on the original face index. Hopefully that makes sense. We're going to assume there's already a UV map. We're editing because this isn't creating a new UV map, it's just editing an existing one. So we take our UV name and we're going to get that named attribute, which should be a vector. And we're going to take our array element with the captured index, and we're going to split all of the edges. So that separates... this is a bad example because it doesn't have enough geometry, so let's just fix that real quick. We'll make a second little bit here and scale it down by half so that we have two different UV areas that we're working on, for an example. So right now, when we come into this node group, this whole mesh is connected. It's one piece. If you looked at the mesh island index, there'd just be one index and it would be 0. Once we split it apart, we actually have, 16 different mesh islands, one for each face, basically. And then we're going to set the position of the actual geometry to where it exists in the UV map. So you can see this is rotated oddly for some reason, but that matches our UV map. If we go back in here and look at the UV map, that's what our UV map looks like. Once we've done that, we're going to make a sort of a big assumption that the mesh islands are disconnected, that they're not overlapping. This is actually a flaw with this node group and this way of calculating these offsets, because as I've discovered, I don't remember if it was with this node or another node, your UVs aren't always laid out in such a way that none of the adjacent separate pieces touch each other. Anyway, so bear that in mind. Anyway, but I merged by distance to connect the parts that are together back together. So that means instead of having 16 mesh islands, I now have 2. Obviously, if these were next to each other, like if this corner touched that vertex there, it would get merged into one, and then all of a sudden this doesn't work anymore. So that's why it's kind of flawed. But in a large number of cases it will work, but and you can work around it just by moving things slightly, but it is a flaw with it. Anyway, once it's all merged together and I have 2 mesh islands, I can split the islands into separate instances based on that island index. So now I have 2 instances, same as the mesh islands. And once I have instances, I can do a bounding box on each instance separately and calculate the size of each instance in the mesh. And the way you can do that is if you have instances and you do a bounding box on it, it does a bounding box per instance rather than one large bounding box. And if you didn't realize that, to turn it into a mesh, you can evaluate specific vertices of those 2 cubes, because you know they're going to be cubes and they're going to have, they're both going to have 8 vertices. You can look at the first one and the last one of each set of 8, and those will map to the instances in sequence. So the first 8 vertices will belong to the first instance, and then the second 8 vertices will belong to the second instance, and so on. So if you just offset what vertex you look at, the index of which vertex you look at, by 8, and look at the 0th and the 7th vertex in each group of 8, you get the minimum and maximum positions of that instance's bounding box, if that makes sense. So that's all this is doing. And then having the size, I can capture the minimum and the maximum vector on each instance separately and realize those and turn them back into a mesh. I guess then I sort them to restore the index in case it got changed. So I sort it by that index value we captured earlier, which means that if the faces got rearranged, I've now restored the order of the faces to what it was before I did all of the separating. Anyways, we're actually done with that geometry. So all of that geometry that we created, and we split the edges and arranged it all, split it into instances based on the mesh island index, and then measured the size of each of those UV islands. That was all just temporary geometry that we're now going to sample from our 3D geometry back outside of this. So you can see here, we pass up one of the instances into our adjustment node group, but we're going to evaluate it using our array geometry up here. So those are 2 separate things, sort of. So we're going to sample this based on the face index, which we can do because if we take the index of our arrayed mesh, it's going to have a number of faces in it equal to the number of faces in one instance in the array times the number of array elements. So if we do a modulo on the index of our arrayed 3D mesh, using the number of moduloing by the number of faces in a single index, so a modulo returns the remainder of a division operation. So if we divide, so in this case we have 16 faces, 16 index values in one instance. So say we're looking at face 32. Well, if you divide 32 by 16, you get 2 with a remainder of 0. So you would be looking at the 0th element of the third instance. So anyway, I don't know if I explained that well or not, but modulo is a very cool math operation to use in a lot of different nodes, so I'd recommend getting pretty familiar with it. Anyway, we're going to sample the index of our single instance that we did all the UV calculations on. We're going to sampling a face index, and we're sampling vectors. We're sampling the minimum and the maximum position of the bounding box of each mesh island in the UV map. Alright, so then once we've sampled the minimum and maximum values off of our UV mesh that we manipulated, we want to actually adjust the UV map on the instance copies that we have. Rotations always happen around a point, and by default that point's going to be 0. So if we want to rotate around like the center of the mesh island, then we need to figure out where that is. The way we figure out where that is we take the size and we divide it by 2, or scale it by half here, and then we're going to add that to the minimum. So the minimum plus half of the size is the center of the bounding box of a mesh island, if that makes sense. So this value here, that's a point that is the center of that given UV island. And so that's going to go in the center of our vector rotate node. This is our actual UV map from way back here. The UV map's the vector to be rotated. The minimum plus half of the size is the center of the rotation. And then we're just taking the Z component of the rotation because anything else isn't guaranteed. Well, anything else wouldn't work on the UVs, and figuring out how to convert another rotation would be complicated. So the rotation's also slightly limited in that way. Depending on whether we're using the rotation or not, we pass a value through this switch node. Once we've rotated the UVs, we need to offset them based on this UV offset value. The way we do that is we take that position, so the 1, 0 in this case, we're going to multiply the size of our UV island bounding box times that position offset value that's passed through from the parameter here, just like we do for the relative offset of the 3D mesh at the beginning of the array node. Then we're going to multiply that offset vector by which instance we are in the array. So the first one is going to be 0, it's not going to move at all. The second one will be 1, and it will move over 1 size scaled by whatever offset value you provide. So the way we do that is we have our index inputs. There's 2 of them because I use this same node on like the array 2-dimensional, where the y offset is controlled by the y array index rather than both the same. But in this case they're the same, so because out here I plug the same value into both the x and the y. Anyway, we multiply the offset by the index of which instance we are in the array, and that means that each successive array element gets their UVs moved over further than the previous one. And then we just add that offset to the UVs that were either rotated or not, depending on the switch. And that is the UVs that come out. And then as a final thing, I also output the size, this first value we calculated here. I don't think I use that in this node. I think I used that in the array 2D node for something. Then all I do is I store that value on the mesh, on the face corner. It's a 2D vector on the face corner with the name of UV name. And then if adjust UVs is on, we output that. And you can see in this case it works perfectly. This smaller UV islands up here, which have the bigger texture scale, tile perfectly, and the smaller one at the bottom also tiles perfectly. If you turn off merge verts or realize, things get wonky, and if you turn off adjust UVs, also gets wonky. So, and then finally, this just, if there's nothing coming out, this just outputs a warning message. So that is how the array 1D node works, all of the things that make it up. Going through it, I found a couple things I could probably improve on. I think these nodes should come after this one, just because that means there's like 2 less nodes that have to be evaluated, even though they probably don't do anything. And yeah, the way I calculate the UV islands, which UV islands are, is slightly flawed, because if 2 of the vertices in 2 separate islands happen to share the same location, then they would be considered one UV island. So those are 2 possible areas for improvement. A better way I've come up with of doing this, that I've used in some other nodes, hasn't made it into this one yet, is to, rather than splitting all of the faces, look at the mesh and figure out which edges in the mesh have face corners with whose coordinates don't match up on the UV map. So you look at the UV map, you look at each edge, and you say, does face corner A match the coordinates of face corner B? If they don't, it means that edge should be split. So you have 2 pairs of corners for each edge for matching faces. But yeah, UVs are not my favorite thing to do. Always involves way more nodes than you think it should. And there's always weird edge cases. So in one of my utility nodes that I have here, I have the set position plus UV node. I essentially wanted a feature that was similar to correct face attributes. However, to make that possible, I had to manually do all of this matrix math before they had matrices in and transforms in that they added in 4.2 now. So anyway, my point is simply that you can do a lot of stuff with the UVs, but there's not a lot of tools to automate parts of the process yet. They don't have very robust nodes specifically for editing UVs, so a lot of it ends up being manual stuff with math and vector math nodes. So anyway, I think I've rambled on long enough about that. If you're interested in any of my tools, anything about that, there's information on my website. All of the links for everything is in the description. Feel free to join my Discord server. There's a link for that in the description too. You can ask questions there or share what you're working on, anything like that. And yeah, that's all I've got for this one. Thanks for watching.